Everyone. Today we're starting a new chapter, so we're skipping ahead here to chapter 18, and this chapter is all about free energy and thermodynamics. So I know some of you weren't really fans of thermodynamics before, so if you feel a little bit rusty or like you need to go back and review thermodynamics, that started in chapter 6, I believe. So definitely go back and take a look. Otherwise, let's go on. So really our question for this chapter is, what drives chemical reactions? Now, the driving force behind chemical and physical changes in the universe is a quantity called entropy. So entropy is related to the dispersion of energy. So things naturally want to become more spread out. Sometimes we say it's more disordered. So nature tends toward that state in which energy is spread out to the greatest extent possible. Now, just a little bit of review. From chapter 6, we had gone over the first law of thermodynamics, which told us that the total energy of the universe is constant. And now in this chapter, we're going to add two more laws of thermodynamics. So the second law of thermodynamics has to do with that term entropy. For any spontaneous process, the entropy or disorder of the universe increases. So the world around us is, in a way, constantly in chaos. And right now that definitely feels true. So you could think of it as we're following entropy right now. The third law of thermodynamics tells us that the entropy or disorder of a perfect crystal at absolute zero, or 0 Kelvin, is 0. So that tells us that a perfect crystal at the lowest possible temperature will have 0 disorder, or 0 entropy. So we're going to talk about all three of these different laws as we go through this chapter, but we're more so going to focus on the second law of thermodynamics, and maybe a little bit on the third law of thermodynamics and the first law. All right, so when we're thinking about energy, remember, has to be conserved. So again, the first law of thermodynamics, the total energy of the universe is constant. So let's say that we're recharging a battery and it has 100 kilojoules of useful energy. Now, if we want to, let's say, use 100 kilojoules of energy from the battery, we actually have to put in more than 100 kilojoules of energy to recharge the battery. And this is due to the second law of thermodynamics. So every energy transition actually results in a loss of energy, or energy that we can't directly use. So maybe that energy is lost as heat. So it's thermal energy that just goes out into the universe. We can think of this as an energy tax that's demanded by nature. So on the right-hand side, we have the example of a light bulb. And the main purpose of a light bulb is to light up a room, right? But in general, if we have 100 watts of electrical energy going into our light bulb, only 5 watts are emitted as light, and the other 95 watts are dissipated as heat. And that would be our energy tax for this system. So it is really hard to create a perfectly efficient system where all of the energy going into the system is being used in a way that we want it to be used. Unfortunately, there's a lot of energy that's just wasted, essentially. Another example I like to use a lot is a refrigerator. So the refrigerator's main purpose is to keep food cold, but we have so much energy going into a refrigerator, and a lot of that energy is actually being dissipated as heat, ironically. Only some of the energy used by the fridge is used to cool food. So we would love to have a perfect system where all of the energy coming in is used to cool our food because we'd have to use a lot less energy, right? But unfortunately, that is not the case. And again, this all has to do with that second law of thermodynamics. So for any spontaneous process, the entropy of the universe increases. So all of the heat that's being dissipated by, for instance, this light bulb, that is going to create more disorder in the universe. So a lot of this stuff is more conceptual, so it can be a little tough to digest. So don't worry if it's a little overwhelming. But here we have a couple of different ways that we could use to heat up, let's say, a house. So the first way we could heat up a house is by using natural gas. And so if we burn natural gas, that will produce heat, and we will have, again, a heat tax. But there's really only one step there. We just, light up some natural gas, it produces heat, and we heat up the house. But then in the second step down below, we could burn fossil fuel to produce energy in order to make some steam. And then that will produce energy to generate electricity, which will produce energy to transmit electricity, which will energize a heater, which will then heat our home. And that's a lot of steps, right? And with each step, we have a heat tax. And so we're going to lose a lot of heat or a lot of energy throughout that whole process. So fewer steps will generally result in a lower total heat tax. And a lot of scientists now are trying to come up with more efficient or energy-saving ways to, for instance, heat a home or, cook food or drive our cars. There's a lot of science going on behind those different areas. But again, just tying this back to thermodynamics, the more heat tax that we have, the more disorder in the universe. So that has to do with the second law of thermodynamics. So let's talk about spontaneous processes. A fundamental goal of thermodynamics is to predict spontaneity. Will a reaction occur spontaneously? So a spontaneous process is one that occurs without ongoing outside intervention, like work. Non-spontaneous processes, on the other hand, require energy input to occur. So a spontaneous reaction, for instance, is a reaction that just occurs on its own. It doesn't need heat or it doesn't need, an outside force in order to occur. Whereas a non-spontaneous process or reaction would require some heat in order to occur, or some energy input of some sort. So thermodynamics predicts whether a process will occur under the given conditions. And spontaneity is determined by comparing the chemical potential energy of a system before the reaction with the free energy of the system after the reaction. And we'll talk more about free energy later on. But essentially what we're saying is we're comparing the initial point of a reaction to the final point of a reaction. So remember from thermodynamics a long time ago, that's called a state function. So spontaneity just depends on the initial state and the final state of a reaction. All right, so in general, if the system after the reaction has less potential energy than before the reaction is called thermodynamically favorable. So we're trying to go from a high energy state to a low energy state. So this is kind of similar to our energy diagrams from before. Now, spontaneity does not relate to the rate of a reaction. So a reaction can be spontaneous and slow. So just because a reaction occurs without any outside help doesn't mean that it occurs quickly. It could occur really slowly. So one example is the conversion of diamond into graphite. So graphite is actually more stable than diamond as a compound. So the conversion of diamond into graphite is spontaneous. So this energy diagram would look like the one we just drew, where diamond would be or have higher potential energy and graphite would have lower potential energy. So this would be a spontaneous process. However, this process is really, really slow. So even though this occurs naturally or spontaneously, that doesn't mean that it's a quick reaction. It occurs really slowly. Now, a catalyst could speed up the reaction, and it's not going to affect the spontaneity of the reaction. So again, just to summarize, kinetics has to do with speed. So we just covered that in chapter 14. And then thermodynamics is more concerned with the initial and final states of the reactants and the products for a reaction. So kinetics is kind of its own thing, and then thermodynamics is sort of off on its own. So they're a little separate from each other. All right. Now, any spontaneous process is irreversible because there is a net release of energy when it proceeds in that direction. So if we wanted to go in the reverse direction, we would need to provide maybe some energy, for instance. And then a reversible process will proceed back and forth between the two end conditions. So if a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. So as an example, the rusting of iron is spontaneous. Iron just naturally reacts with moisture and oxygen to produce iron oxide. So you'll notice that we're going from a nice shiny car to a rusted car. Now, if we wanted to reverse that process, we would probably need to use some chemicals to shine it up, remove that kind of outside layer of rust. So we would have to put some work in. So the reverse process would be non-spontaneous. So again, spontaneous processes occur because they release energy from the system. And again, most spontaneous processes proceed from a system of higher potential energy to a system at lower potential energy. So most spontaneous processes are exothermic, although we'll see some examples where they are endothermic. So I'm going to redraw that energy diagram. So let's say we have our reactants reactants, and they have a pretty high potential energy, and then the reactants react, and we have products at the end with a lower potential energy. So in chapter 14, we talked about how the difference between the energy of the reactants and the activation barrier, that is the activation energy. But then if we take the difference between the reactants and products, that actually gives us the amount of heat that is released. So delta H, or enthalpy here, would be negative. And this would be an exothermic process. And again, most spontaneous processes are exothermic. But there are some spontaneous processes that proceed from a system of lower potential energy to a system at higher potential energy. So they are considered endothermic. So I'm going to draw that same energy diagram, except this time the reactants have a lower potential energy than the products. So this time the activation energy is quite high, because remember, we determined the activation energy by taking the difference between the reactants and that energy barrier at the top. And then delta H will be the difference between the reactants and the products. So in this case, it's actually going to be positive. And that means it is endothermic. So how can something absorb potential energy yet have a net release of energy to the surroundings? So how could an endothermic process be spontaneous? So if you've ever watched ice melt, melting is an endothermic process. And ice does spontaneously melt above 0 degrees Celsius. So this is an example where we have an endothermic process that is also spontaneous. So when a solid melts, the particles have more freedom of movement. So as we go from our solid state, where everything is in a fixed, rigid position, to our liquid state, the particles start to move around, they can rotate, they can maybe vibrate more. So more freedom of motion increases the randomness of the system. And when systems become more random, energy is released. And we call that energy entropy. So again, this is a process where the ice is absorbing energy, but overall there will be more entropy as a result. And so we're following the second law of thermodynamics. We're seeing an increase in entropy. And so this is a spontaneous process. Now, another example is the evaporation of water. So let's say we take that liquid that we got from our ice and we heat it up, or I guess it naturally heats in this case. So let's say it's hanging out by a hot spot somewhere, and it turns into a gas. Remember, gases have a lot of kinetic energy, but additionally, there's more freedom of movement for a gas compared to a liquid. So we do see an increase in entropy, even though the liquid was absorbing heat. So the overall process is spontaneous, even though it's endothermic. So on the website, I've posted the worksheet for chapter 18. And let's just work on worksheet problem 1. Let's determine which of these processes is spontaneous. And some of them might be debatable. So A, we have the combustion of natural gas. So would we consider that a spontaneous process or a non-spontaneous process? So another way to think of this is, do we have to put energy into the system in order for it to occur? So this is where this is a little debatable, because natural gas can combust on its own if it's hot enough or given enough energy. Now, if we're considering, for instance, a gas stove, we do have to provide a source of energy in order for it to combust. So we could argue that, depending on the situation, the combustion of natural gas could be spontaneous. I'm going to say here, let's say we have a gas stove. So we have to provide energy. Oh, my pen is freaking out. In order for the natural gas to combust. So in that instance, it would be non-spontaneous. But again, natural gas can combust on its own too. So that is possible. Now what about B, the extraction of iron metal from iron ore? So do we have to put work into that system in order to extract iron metal? Yes, we would need tools to extract the iron metal. So this would be, or this would require outside forces. And so it is non-spontaneous. All right, what about C, a hot drink cooling to room temperature? Is that spontaneous or non-spontaneous? So hopefully you said spontaneous, right? Because this just occurs naturally. We don't have to put any work in order for a hot drink to cool unless we put it in the fridge. If we put the hot drink in a fridge, then we're doing work to cool it down, right? But if we just leave a hot drink out on a countertop, it will naturally cool to room temperature. So this would be spontaneous. And then D, drawing heat energy from the ocean surface to power a ship. Do we think that's spontaneous or non-spontaneous? So would that require outside forces? So this would require work in order to power the ship. So if we're trying to draw heat energy up, we would need something to do that for us. So this would require an outside force. So this would be non-spontaneous. Okay, so hopefully that helps a little bit with understanding spontaneous versus non-spontaneous processes. In the next lecture, we're going to start discussing entropy in more detail. We'll also eventually get into free energy, which is a little bit different but still related to entropy and enthalpy. So I will see you in the next video.